Hello again, everybody. Today we are going to build on the discussion we had in the last lecture. We are going to consider this electron in a solid, in a periodic solid, meaning that the potential that the electron sees, which is because of all the nuclei, are periodic. It's a periodic function. But before we do that, we're going to turn off the potential. When we turn off the potential, basically it means that we have a constant or zero potential that the electron sees. Under those conditions, the solution is trivial. It's the free electron solution for which the energy is going to be equal to h bar squared k squared over 2m, meaning the energy is going to be quadratically dependent on the wave vector k. And then we turn the potential on gently. Now the electron is sitting in a periodic potential, and then we ask the question, what happens to the energy versus k dependence? We are going to add a little mathematical rigor to all of this today, and we are going to see how this simple, trivial, quadratic dependence on k of the energy is going to get adjusted, or it's going to get changed because of the periodic potential. So this may be a good time to refer to this concept called the Kronig-Penney model, which many standard quantum mechanics textbooks have. Okay, first let's consider the case when our periodic potential has been turned off, under which situation our electron is completely free. So there it is, under these conditions, when the periodic potential is turned completely off, the energy, as I mentioned earlier, is going to be quadratically dependent on k. E equals h bar squared k squared over 2m, and our energy versus k plot is going to look like this, a very simple parabola. Of course, we do know that there are these nuclei which are periodically arranged, let's say with a lattice parameter a. It's just that temporarily we have turned the effect of the nuclei off. And so, because we have a periodic situation with lattice parameter a in real space, the lattice parameter in reciprocal space is 2 pi over a, which means we will have this thing called the Bravon zone, which we discussed in detail last class. And the size of the Bravon zone, the length of the Bravon zone, at least in a 1D case, is going to range from 0 to 2 pi over a, or minus pi over a to plus pi over a. And then we can do this thing called zone folding because of all these nice symmetry properties that our reciprocal space implies, as we discussed in detail again in the last lecture. And here is the zone folded situation. This is the stuff that you see in red, right? So this is exactly the same parabola, except that some pieces of the parabola have been translated, as we discussed in the past, right? So just as a reminder, our Bravon zone is extending from minus pi over a to plus pi over a. So within that region, the original parabola stays as it was. But the other pieces of the parabola, for example, this piece over here can be translated to the left by 2 pi over a, and this piece becomes this piece now because it has been translated. Likewise, this piece has been translated to the right by 2 pi over a, and that becomes this, and so forth. Right? So the red line that you see over here is really the zone folded parabola, the zone folded energy versus k dependence of our free electron. Now we turn the periodic potential on, and when we do that, we encounter some changes to this zone folded situation. In particular, gaps begin to open up at these locations. So there we go. Gaps have opened up. And what you see on the right in red lines is essentially the same as what you see on the left in red lines with gaps opening up in these locations. That's what the periodic potential does to our to the electronic states, electronic energies of our electron. In principle, what is going on is when our electrons have wave vectors or wave numbers close to plus or minus pi over a with the corresponding wavelength, of course, they are going to be scattered by our periodic potential. Bragg scattering by the periodic potential is what happens. And that leads to certain energy values becoming disallowed. That's why these gaps open up. Okay, now let us write down the specific equation that we wish to solve. So here is our Schrodinger's equation appropriate to our electron, and of course the potential V of R in the Hamiltonian is a periodic quantity. And when V of R is periodic, our Bloch's theorem, which we encountered in the last lecture, requires that our wave function psi of R has to have a certain form. And here is that form. So the wave function psi k of R has to be a product of two quantities, e to the I k dot R times quantity uk of R, and uk of R has to be a periodic function. So if the potential V of R is periodic, it does not mean that the wave function has to be periodic, but the wave function has to be a periodic function times a phase factor e to the I k dot R. And of course there are several possible values that k can take, and it is for this reason that our wave function has a subscript k. So the wave functions are all indexed by k, and likewise since there is an energy associated with each wave function, our E also has the subscript k. There are many ways to proceed from here. This is a good time to look up this thing called the Kronig-Penney model that I mentioned earlier on. Many standard quantum mechanics textbooks would deal with the Kronig-Penney model. Here what we are going to do is we are going to use the route provided by Fourier transforms. So we are going to expand two key functions using Fourier series, right? So we have our periodic potential, meaning a potential V of R is periodic. So we're going to expand that in a Fourier series, and our wave function is a product of e to the I k dot R times a periodic function, and so we are going to expand that periodic function uk of R as a Fourier series, and then we're going to proceed from there. Okay, so here are our two Fourier expansions. So V of R is expanded as a sum over plane waves, and our V G prime, these are what we call as our Fourier coefficients. It's quite easy to understand what this Fourier transform really is, Fourier series really is. Bear in mind that e to the I g dot R is essentially a sum of a sine and a cosine. Right? So what we are saying is that we have this function V of R, which is periodic, and because it is periodic, this function can actually be written as a sum over a number of sines and sine and cosine waves, right? And the coefficients of our sine and cosine waves are these V G prime terms. So having a knowledge of V G prime, all the V G primes, is basically equivalent to having a knowledge of the function V of R itself, right? So that's really what the Fourier series is in this context. Likewise, we have the other periodic function uk of R, and since both the uk of R and V of R have the same underlying periodic spacing, they can both be written as a Fourier series with the same set of reciprocal lattice vectors G. However, since we are going to have both V and U buried in that psi in the same equation, we want to distinguish between the two sums. and because we want to distinguish, we want to keep track of the both the sums separately. We want to make sure that we use a different set of indices for our reciprocal space expansion coefficients, and so we're using G over here. So using G prime over here and G. Note that both sets of reciprocal space vectors are identical, are the same. We are drawing from the same pool of reciprocal space vectors, in other words. Same set of sines and cosines, in other words. Right? So V of r is written over, as a Fourier series, with the Vg prime being the Fourier coefficients, and likewise our Uk of r is also written as a Fourier series, and UKG is our Fourier coefficients. So we are going to take these two sums and stick them into our Schrodinger's equation, right? And we're going to proceed from there. So that's the basic idea. Okay, so here is what we have. So we took the two Fourier expansions and stuck that into our Schrodinger's equation, and we get this cumbersome looking equation. Now let us note something important. Let's take a look at this quantity here. This is of course our wave function psi k of r, which is a plane wave part, which has a plane wave part e to the I k dot r, the phase factor, times the periodic function uk of r, which has been written as this. For the purpose of the algebra that will follow, it actually becomes useful to take this quantity inside the sum, and when we do that, the two exponentials can actually be combined. So this is what I mean. So this is what you have, and the same thing applies to this quantity over here as well. So next what we do is we take this stuff that's outside our square brackets and take that inside, and essentially this means that this quantity over here is going to operate on this, and this quantity is of course going to just multiply that, right? So this quantity is taken inside our square brackets, so you'll have this quantity over here and this quantity over here, right? And when our del squared operates on our wave function over here, something very nice happens. The first time it operates, you get I times k plus g, which gets pulled out of this summation. And then the second time del operates on it, you get another I times k plus g. So when you multiply these two things that got pulled out, you get minus k plus g squared. So when this quantity here operates on our wave function, you essentially end up with h bar squared over 2m times k plus g squared, times of course this whole thing. That's what happens to the first term. Now when this term over here gets multiplied to this quantity, you get a double sum. So you keep that in mind. And then on the right hand side, once again you have your ek multiplied by the same thing. So what you will see is that on the left hand side you will see two terms, and both terms will involve summations. And on the right hand side you will have just one term, which will involve this summation over there. And now by equating the left hand side and the right hand side term by term, you get a very nice looking equation. So there it is. I leave the actual steps involved in going from this equation over here to this compact nice looking equation as an exercise. We can also rearrange this particular equation up here in the following manner, which looks even more compact because we have grouped the two terms that involve UGK, and so we have pulled that quantity out. You see this term here and that term there have UGK, explicitly showing up. So we kind of group the two up and pull that term out, and we have this nice compact looking equation. In case you're wondering how this u k in here got this subscript g minus g prime, it's a matter of keeping track of the various terms of the three different summations. Again, a little bit of an algebraic manipulation is involved in singling out and identifying how to create this particular sum, but again I'm leaving that as an exercise. But okay, in the end we have this equation. Bear in mind that in principle this is actually an exact equation for a single electron encountering a periodic potential. To proceed from here, we are going to make some simplifying assumptions. The first assumption that we will make is that the only non-zero terms of our Fourier expansions are for the g equals 0 and the g prime equals 0 terms. Right? So let us very quickly go back to our Fourier expansions. Okay, there it is, right? So here was our original Schrodinger's equation at the top of the slide, and then we resorted to the Fourier expansion of the periodic potential and the periodic part of our wave function, right? So in principle, note that these two series are in infinite series, right? But in practice we have to truncate them. So the first approximation we are going to make is that we are going to truncate the series to such an extreme extent that the only terms that are retained in the two sums are the first, the zeroth order term, right? The g equals 0 term. Sorry. So in this summation we retain only the g prime equals 0 term, and in this summation we retain only the g equals 0 term. And essentially the first term of these two sums. Okay, so let's go back to our equation over here, and we're going to make the assumption that we retain only the g equals 0 and the g prime equals 0 terms in this equation. And when we do that, it turns out that we are taking recourse to what is called as first order perturbation theory. Okay, so we go to our equation over here and set everything, all the terms for which g or g prime is not equal to 0 to 0, and here is what we get. Okay, here we go. So so note that this term here is over here. Everything for which g is not equal to 0 is 0, and so this term became that, and of course this term became that. So now you see that both on the left and the right hand side we have this uk of 0, which can be cancelled out, and we get our final result. So there it is. So Ek is equal to h bar squared k squared over 2m plus v naught. Note that v naught is a constant, right? It's just a number, it's a constant. And so what we have actually recovered is just the free electron result. So if we resort to first order perturbation theory, meaning that if we say that the only non-zero terms of our Fourier expansions are the g equals 0 and the g prime equals 0 terms, then we basically get our free electron result. So this is hardly interesting. So in order to see something interesting, we need to go beyond first order perturbation theory, meaning that we need to include some other terms in the Fourier series. So what we are going to do now is exactly that. So now, in addition to the g equals 0 terms that we assumed to be the only non-zero terms earlier on within the first order perturbation theory, we now assume that the g equals g prime terms are also non-zero. All other terms are 0. Right? So you have these two Fourier expansions, and the first terms of the two Fourier expansions are non-zero, and then there is the special term for which g and g prime are both going to be the same, and so those two terms of the Fourier expansions are also non-zero, and all of the other terms are 0. right? So we are going a little bit beyond what we just did earlier within the framework of first order perturbation theory. When we do that, we begin to see something interesting, and of course, bear in mind that we make these assumptions so that our equation that we wrote down earlier, which I said was an exact equation in principle, becomes tractable, right? So that equation is exact in principle, but it is still complicated. And for us to see something interesting, for us to tease out some interesting behavior out of that equation, we need to make these assumptions. That's exactly what we are doing. The first set of assumptions that we made did not lead us to anything interesting. We found something that we already knew because the level of assumption was too low. So now we are saying, okay, let's make it a little more sophisticated, but we want to make it sophisticated, but at the same time, we want to also make sure that our basic equation becomes solvable, tractable analytically, right? So when we do that, when we make this new assumption that the g equals 0 as well as the g equals g prime terms are the only non-zero terms of the Fourier expansion, we get the following result. Basically, we get a quadratic equation, which when you solve, you get this result for the energy. So here it is. So I again leave this as an exercise to figure out how one would arrive at this rather cumbersome looking result from the assumption that I'm stating up here. Right? So as I said, you get a quadratic equation when you impose this assumption, and solving that quadratic equation will actually give you this result. And note the plus or minus sign here, meaning that there are two separate sets of solutions that you would get. So you can actually plot E versus K, right? So you see Ek is a function of K everywhere, and so you could in principle plot E versus K, and because of this plus or minus sign over here, you would get two branches, right? You will get two sets of solutions. You will get two branches. How is that going to look? Right? So let's take a look at what you would get if you simply plotted Ek versus K. Not surprisingly, you will get this type of a situation, this type of a result if you were to plot your Ek versus K. Of course, I've done the zone folding for you already, and we can also estimate the value of the gaps that you are seeing over here. And these gap values can actually be verified analytically by making appropriate substitutions in our energy versus K expression over here. And of course, you see different strands or branches or bands. These are the different bands of our band structures. You see, we have a rudimentary version of our band structure with gaps and so forth. Of course, in this particular case, I have done the zone folding for you, and I leave it as an exercise for you to choose different values of G, and for each value of G, create your band structure plot using this expression over here. Note, of course, that we do not choose G equals 0 because this is something that was done already within what we called as the first order perturbation theory. And anyway, the G equals 0 term is already contained over here. So the values of G that you would choose would be integer multiples of 2 pi over a. And so you got your G here, and of course you got the G subscript over there. And so for each choice of G, you also need to choose some value of Vg. So for plotting purposes, you would set some convenient value for V0 and the various values of Vg. And when you set G equals 2 pi over a or minus 2 pi over a, you would get these two bands, right? Note that for each choice of G, you will have two solutions corresponding to the plus and the minus signs over there. And so for each choice of G you will get two bands, and for G equals 2 pi over A, you would get these two results. And when you said G equals 4 pi over A or minus 4 pi over A, you would get the higher lying bands, and so forth. Now you may want to dig a little deeper and ask the question as to what the wave functions corresponding to these energy levels would look like. And that is also something that is easy to do for at least special choices of our K. For example, this one here and these 2 points at the zone boundary. I should of course note that this value of K corresponding to the zone boundary is really in this particular case pi over A, and likewise this is minus pi over A, right? Okay, so for special choices of K, such as this one, this one, this one, and this one, etc., we can actually figure out what the wave function is going to look like. So again, I'm going to leave that as an exercise to figure out the exact form of the wave functions. All you really need to do is to choose the appropriate value of G and the appropriate value of K in the expression for the wave function. Remember that we wrote the wave function as a Fourier series, and we decided to keep only two terms, right? The G equals 0 term and the G equals G prime term, right? So there are only two terms that remain in the Fourier expansion of the wave function. So your wave function will contain two terms, one corresponding to G equals 0, another one with the index G, and for various choices of G and for various choices of K, you can actually write down the expression for the wave function. And when you do that, it will give you a feel for how the wave function is going to look. And we are just going to visualize. I'm just going to create schematic drawings of how the wave function would look in these special points right now. Okay, here is how our wave functions are going to look qualitatively. It's a little bit busy. It's a lot of stuff in here. So let's just walk through this step by step. The wave function at this lowest energy situation over here is going to be like a constant value, right? Meaning that the wave functions, the atomic orbitals from each of our atoms are just going to simply add up, leading to what we are very familiar with, something called the bonding combination of the molecular orbitals, of the atomic orbitals, right? So that is the situation at this point. Now let's take a look at how the wave function is looking at this point, right? So here is what we have. So what is plotted here is a wave function, not the modulo square of the wave function, right? So the modulo square of the wave function is the charge density. So what is plotted here is really the wave function, and you can see the nodal pattern, right? So this clearly looks like our antibonding combination. If you go back to one of our previous lectures, we talked about how when you bring in a lot of atoms together, we use the example of lithium, we bring in a huge number of atoms together, and we try to list all the different possible combinations, and at the very low end you will have the bonding combination, and at the very high end of the energy spectrum you will have a completely anti-bonding combination, and you see, this is what it is. So our nearly free electron model is actually automatically giving us a solution that looks like a completely anti-bonding combination of s orbitals through and through, right? So you have nodes at every point, and of course if you plotted the modulo square of this wave function, you will get the charge density. You will get stuff like this, right? Meaning at the bond center you have a depletion of electronic charge, so which is what makes it anti-bonding. Something a little bit different happens as you go to the higher level over here, right? So that again has essentially the same symmetry as this one, So this wave function over here has the same symmetry as this one in terms of the nodal structure, except that the nodes are now on top of the atoms, right? Now, if you if you imagine, if you visualize a little bit, you will see that this kind of has something like a p symmetry, right? So if you take this particular atom over here, the wave function is positive on this side, and the wave function is negative on that side. Likewise, if you take this atom, it's a negative on this side, and this is positive on that side, right? So this appears to have something like a p symmetry. So you can visualize, you can take this particular atom here. It has a p orbital with a positive lobe and a negative lobe, and likewise you have an atom here with a p orbital with a negative lobe and a positive lobe. So negative and negative reinforce, and positive and positive reinforce, and so forth, right? So you're getting something, a pattern that is reminiscent of a collection of p orbitals, bonding combination of p orbitals. Likewise, you can go up over here and visualize the wave function. It's going to look like that. Note, of course, that as you go up in energy, it is as though the wavelength is decreasing, as it should, right? So this picture over here is somewhat similar to this picture, except that it has half the wavelength, right? And once again, you see there is a certain characteristic nodal structure, right? In fact, there are more nodes. As you keep going up and up in energy, you will have more nodes. And likewise, when you go up to that situation over here, once again, you have this type of a situation. And again, I try to explain this in terms of p orbitals. Let's now take a random atom. Atoms are, of course, represented as black dots, right? So you take an atom over there. You see, this is like a p orbital. So positive lobe and then the negative lobe of the p orbital. Likewise, if you take this atom here, negative lobe, positive lobe, right? This clearly looks like a anti-bonding combination of the p orbitals, because you see you have a positive lobe here of the p orbital hitting against a negative lobe of the p orbital of the next atom. So positive is coming together with the negative, and likewise on the other side you have positive with negative, and so forth. So this is a combination of p orbitals that are anti-bonding in nature, and so forth. So you see, all we have drawn here are just waves, and the reason we have a wave-like structure over here is, of course, because we started off with the free electron situation and gradually just turned on the potential just a little bit, so that we are able to keep only one other Fourier component other than the g equals 0 term, right? So it's which is why it's called the nearly free electron model. It's pretty much the free electron model with a little bit of a twist. So and for that reason, our wave functions look wave-like, right? Plane wave-like. Nevertheless, we have come to the conclusion that we have several bands. We have this k quantity, reciprocal space quantity, labeling our wave functions, and depending on the specific value of k and depending on the specific band, you have a characteristic nodal pattern. And if you just stick with just the bottom band just for a second, you see that there are several values k can take, a large number of values k can take, and each value really indexes a nodal pattern for the wave function, right? So if you are at this point over here, there are no nodes. That's the bonding combination. If you are at this point over here, if k is equal to that, then you have a ton of nodes. You have, in fact, as many nodes as there are atoms, right? Between any two atoms, you have a node. And for all intermediate values of k, you will have varying number of nodes. And this is something we already saw in the previous lecture. Towards the very end of the previous lecture, I drew pictures soon after we discussed Bloch's theorem as to how we expect the wave functions to look. So in that lecture, towards the end of the previous lecture, we actually drew schematics of the wave functions for various values of k for this band. Now we have just listed how the wave functions would look for even higher bands. So we have an entire band structure now. But this band structure is a result of starting from the free electron picture, right? So we assume that the electrons are completely free, and then we turn this knob and make them slightly bound, and we get a band structure which is different from the parabolic free electron behavior. We could start from the other extreme, namely we can assume that our electrons are super tightly bound to our atoms. In fact, in the limiting case, our electrons of a particular atom are completely bound to that particular atom, right? And then we turn a knob and release our electrons a little bit, right? Make them slightly free, right? In today's lecture, the electrons were almost entirely free, slightly bound. The other extreme is we start with a picture when the electrons are completely bound and we turn this knob and make them slightly free. That procedure, that method goes under the name of tight binding, right? That's the tight binding theory, the tight binding model. And we can come from the tight binding model and create the band structure too, and that will provide us even more insight into the nature of the band structure and the nature of the wave functions. And that is going to be the subject of our discussion in the next lecture. Thank you very much.